Today, inshallah, we will take lecture 3, software consideration. As we have seen before, we have a physical world and we take the physical signals from the outside world and we use sensors and transducers to convert the physical signal to electrical signal. Then after we take this electrical signal, we make some conditioning and then use analog to digital conversion to transfer the data in a digital form to the computer. Actually, we will deal with the computer in this lecture. Previously, we have seen this part of computer in a hardware in the previous lecture, and today we will study how software is going to affect real-time dealing with transducers and sensors. How the software will affect the real world dealing with transducer and sensor. So, for example, we have here the furnace controller, and you know, the furnace controller is like we want some uh, temperature to be fixed. Uh, After the temperature is reached, we have a switch. This switch is controlled by a computer. When the temperature is reached, the switch is off, and then when after some cooling down, the temperature is down, so the switch is going on again to heat up again. So this is kind of like any refrigerator and any controller in the same way in temperature. You reach a specific temperature and then the control will switch on and off the cooler or heater according to which application to reach the specified temperature. We have here the controller. Okay, the controller swing off and on around the mean of the required temperature. And the response time is very important here. We need the response time to be limited and minimum. We need the response time to be minimum. We reduce the response time. It's very important about to talk about today is to have a very small response time. If we have very small response time for the controller, we can say this furnace system is a real-time data acquisition and control system. Okay, so when we have the controller, very fast response and can swing off and on with a fast way and control the temperature, this means it is real-time DA&C data acquisition and control. By the way, DA and C is the same as input output because DA, which is data acquisition, is getting data from the outside world and control is sending signal from the computer to the outside world. So this is exactly the same as saying input output. What are the requirements for real-time data acquisition and control systems? We have a number of factors that affect the response time of a PC. The first one is a high speed and the rates, throughput rates and response time. The PC should be equipped with very powerful processors, which are more than adequate for many data acquisition and control tasks. However, the memory and the input-output systems must also be capable of operating at high speed. This means the computer or the PC should have a very powerful processors and input-output dealing with internal memory. For example, we can adopt the direct memory access technique to be able to make a high-speed application. So high speed is very important to have real-time DA and C system. Determinism. This means determinism is precisely predict every detail in which the system responds to specific event or condition. For example, how much time is taken to deal with interrupt, how much the system is, how much time is needed for the system to switch between tasks. So determinism means the system knows exactly what time needed for each action. Determinism means that the system knows exactly or how much time needed exactly for dealing with each event. This is determinism. And the third requirement is high resolution timekeeping and pacing facilities. This means the computer should have the ability to measure the elapsed time and also be able to distribute the time between input output peripherals. As you know, this scheme is called, I know you studied some of these concepts in operating system subject. uh, uh, this scheme is called the round robin scheme. So switching between tasks and distribute time should be predictable from the system. And when I say system, I mean the computer system, which contains CPU and memory, and the connection between PC and input output. The fourth requirement is flexible interfacing capability. The interfacing is very important part of our real-time systems. That's because the system is dealing with physical world. The system is dealing with physical world. So we have to find the flexibility of having the tools needed to interface with the physical world. For example, the presence of appropriate plugs and sockets and expansion slots. It is not feasible to have a computer system without such requirement. So the computer will be isolated if it doesn't have such requirement for interfacing with the input output. It's like this is the holes. You can see the holes which permit the data to go outside and come from outside to inside. Uh, Also, the flexibility also maybe the capability of transferring data in and out of the computer and using some of the interfaces like PCI and ISA buses, and using this technology, which is direct memory access, and also having bus mastering. This is bus mastering, not bus mastering. This T is error, so it is bus mastering. All these capabilities make the computer flexible and can interface with the outside world without any problem. The fifth requirement is ability to model real world process. The ability to model real world process. This means we have an operating system, and this operating system should be able to handle the input-output process. For example, maybe maybe this is the first time to hear about real-time operating system, RTO. This RTO is like a specialized operating system for the purpose of dealing with physical world. It is fast compared to traditional operating system. It is fast compared to Windows and Linux because it is specialized to be fast and to handle input-output interface. So if we speak about process, we speak about operating system, and we need some kind of operating system that is fast and can deal with the input-output interface without any problem. The last requirement here is robustness and reliability. And of course, these requirements, maybe you can say these requirements are common, and you can find it um, in many systems. Yeah, the system should be robust, means not the integrity is very high, very high integrity, and reliability means that you can have it available for example, 24/7. So these are the requirement for any system to be real-time system, for any data acquisition and control system to be real-time system. So if we talk about the simple, the software inside the PC, how it deals with the physical world. It starts with simple keystrokes and alarm. It starts by alarm. After the alarm is taken by the CPU, the CPU is waiting for pacing signal. The pacing signal is important if you study or if you have studied the computer networks subject, you hear about the start and stop patterns. It is like start and stop patterns. So the pacing signal, after the pacing signal is like saying, okay, can we start transferring data, the physical world here, waiting for this signal to start the transferring of physical world data. So if the computer receives a pacing signal, it starts acquiring data from the outside world, and then start processing this data by scaling, linearizing it, and then taking an action. And this action is called control. The control means the data is coming from the PC to the outside world, and accordingly, we can update or display data and or log the data according to this condition. And this loop continue until the entire data needed from the outside world is taken or transferred to the computer. So this is typical software scheme in any computer dealing with the outside world. Now we start to talk about some systems that need more stringent timing requirement, may restrict time or more strict time requirements. I think you heard about interrupts in your study. Can anybody, one of you, tell me what he knows or she knows about interrupts? Anybody knows about interrupts? What are interrupts? What the meaning of interrupts? Anybody knows? Saeed, Elias, Abdul Latif, Ala, Nadine, are you there? Can you hear me? Abdullah Ahmed, Firial, Hanin, Hanin برضو, Maysoon, Omar, and Zakaria, Khalid. Anybody can answer me? سامعني ولا ايه؟
دكتور سامعك.
طيب, okay, can you answer me? Can you tell me what are interrupts? You study the interrupts. Maybe I will tell you which subjects maybe you passed by with such concept. The first one is operating systems. The second one is microprocessors.
Hello, doctor. Sorry, my mic wasn't working.
Okay, no problem. So again, if you know anything about interrupts, you tell me. Anybody? Elias saying it is used to do another task at the same time. Yes, this is not. This is part of you are saying big circle. The interrupt is part of this big circle. And okay, okay. Let me answer the question. So
دكتور
yes, okay.
دكتور هو عبارة عن feature بالكمبيوتر
أيوة.
limits the temporary interruption of one activity as the execution program, for example, in order to perform another.
And in order to what?
To perform another.
Okay. That's exactly the definition of interrupts. Okay. Thank you, Ala. For the interrupts, I want you to imagine a hospital, and a patient is laying down on the bed, and we have two schemes here. We have a nurse, and this nurse should check this patient every 1 or 2 minutes. So the nurse will go to the patient's room and check his temperature and check his heartbeats, and as you know, other functionality. Every 1 minute, she's doing that every 1 minute. This is going to exhaust the resources. The resources means here means nurse, because the nurse will be busy doing this check. There is another scheme or another solution for this. What is it? It just to put an alarm or to put alert, some kind of alert button beside the patient's bed. When the patients need anything, the patients press the button, and the alarm is heard by the nurse, and the nurse can come to the patient's room and start to deal with the patient. This is another scheme. The second scheme is interrupt. It's like the nurse doing her daily job, and she is interrupted by the requirement from a patient. Because we cannot stay the whole time checking if somebody needs some help. We cannot do that. The CPU cannot continuously checking the input output if they need to transfer data or do something. We cannot do that. It is impossible. The best way is to tell the input output. If you need something, you send an interrupt signal. Just to send an interrupt signal, and the CPU will, by any way or another, you know about it, maybe is interrupted flag or something, like the CPU will check this flag. If it is set, this means the input output needs some job or task. This is exactly what's happening in the interrupt scheme in the computer. It's like the nurse is sitting or doing her daily job, and then she heard an alarm that the patient needs some help. This scheme is not the perfect one because it contains some problems. Like if the nurse is serving this patient and at the same time it is she is interrupted by another patient. So we will deal about such like we have to make priority for interrupts. We will deal with such problems, or I mean, the CPU should have a scheme to deal with such problems. So it is not like model or is like 100% solution. It contains the problems. That's why we say interrupt, and we also should know that the interrupt is we have a normal scheme, normal operation like a main function, and then the CPU is jumping to the interrupt routine and finish the interrupt routine, return it back to the main routine. And I told you about the priority. If we have multiple interrupts, we have to check for the priority or to handle the priority. And of course, I don't know if you know that or not, the system, the operating system services has higher priority, or services have higher priority compared to other input output interrupts. It's like the nurse is serving the patient at the same time she got a call from the hospital manager. This is operating system interrupt. So the operating system services is has more higher priority compared to input output routine. So we have to deal with interrupting the interrupt. It's like two levels of interrupt. Or we can have the interrupt of interrupt of interrupt. It's like you have to deal with this. I will talk about this soon. So in normal operation, this is the main function, and the CPU is serving the main functionality, and the CPU heard that or knows that an interrupt needs help. So the routine is jumping to the interrupt, dealing with it, and jump back to the main routine. Of course, you know that the interrupt here, before interrupt, we have to save everything. We have to save the status, because when the CPU finishes the interrupt, it must return to the same place where it left off. So we have to save the status, go to the interrupt, return back from the interrupt. By the way, this is just returning back from the interrupt. We didn't draw the entire figure. This is just this part when the interrupt is finished and the CPU is returning back from the interrupt. We have two main problems here: reentrant and interrupt latency. Reentrant and interrupt latency. You have to, if you don't understand these two problems, you just tell me, repeat. We will talk about them now. The reentrant means we have an interrupt and the processor is save all the processor registers. That's why I'm telling the, sorry, that's why, that's the reason, the only way you can say this is the only way the processor can have or save the current status, because if the CPU want to go to the interrupt, it should be able to continue from the same place which it left off. So the CPU preserve all the processor registers and refrain from interfering with any hardware devices. This means stop accepting more interrupts, because it cannot continue. It cannot continue the first interrupt and then jump to another interrupt. Actually, some operating system services, they accept, they are preemptive. Preemptive means they cut the current interrupt routine. So care should be taken when calling any subroutines or operating system services. As I told you, the operating system services, when I say operating system services, I mean like the patient and the nurse had a call from the hospital manager. This is an operating system service. Multiple invocation from within interrupt may lead to problems. This is reentrant problem. If it is not well organized, as I told you, it is endless. If the nurse is dealing with the current patient and another patient is pressing the alarm, is interrupting, what she will do? The operating system should tell her what she will do. The operating system should have concrete routines for dealing with such situation, should have ability to handle the reentrant problem. We have some operating system that is not reentrant. They don't have reentrant. They have one routine and they don't change that routine. Even if they have a higher priority interrupt. There is no higher or lower priority interrupt. They have a routine. If they have interrupt, they jump to that interrupt. They cannot be interrupted. There is no reentrant. They finish that interrupt routine and then return back to the CPU thread again. And also the real-time operating system are partially reentrant. And Windows is reentrant. Windows is reentrant. It allows the interrupting an interrupt. That was the first problem, which is reentrant. About the second problem, which is interrupt latencies. The interrupt latency is the time taken for the nurse after she hear the alarm and go to the patient's room and start dealing with the case. The time taken for her to move from her current location to the patient room. This is the interrupt latency. The time taken for the CPU, for the CPU, it means the time needed for the CPU to leave the current thread and move to the interrupt thread. This is time interrupt latency. You can say the delay between interrupt signal and the time of handling the interrupt. The programmer should be able to estimate the maximum latency. This is important for real-time applications. If we don't measure the latency, we will deal with a problem. Real-time means, as I told you about the Fornace, we should be able to have real-time update of the temperature. Windows and DOS are non-deterministic. They have a very high latency as they can respond to operating system service while handling the interrupt. Okay. Oh, yes, I forget to tell you about the DOS. The DOS is responding to the operating system. It takes an interrupt signal from the operating system only the operating system, but Windows allows another input-output interface to interrupt the current input-output interface. Sorry, the Windows permits, for example, if the CPU in Windows, if the CPU is dealing with an interrupt, the system allows another interrupt to interrupt the current one. Okay, this means because maybe you're confused why DOS now we allow it is a reentrant. Reentrant means it talks about the interrupt routines from input-output interface, not from the operating system services. RTOs, or real-time operating system, are designed to reduce interrupt latency. So when dealing with interrupt, we have two problems. The first one is reentrant problem, and the second one is interrupt latency. What about the concurrent processing? Concurrent processing means that for a single threaded computer, this can be done by assigning the data acquisition to a different system. We can move to the next slide to see that. We have multiple processes. We have first process, second process, and third process. The first process is dealing with the first physical process. And the second process is dealing with another process, and third process is dealing with another physical process. And they go to the same cycle as we have seen before. We have interrupt signal and then start acquiring data from the outside world, then analysis, then control, which is moving data from inside to the outside world. So we deal with a complete data acquisition scheme with single physical world, with you can say single input-output device. How to deal with that? The first solution for dealing with multiple processes like that is making a multitasking. Multitasking is a feature in Windows. Let's Windows dealing with the first process, then move to the second process, then move to the third process, and then return it back to process one again for a specific time, and then move to process two for a specific time, and move to process three for a specific time, and then return it back to process one. This is a round robin scheme, as I told you about. This is not multi-processing. You have to understand the difference between multi-processing and multi-programming. This is multitasking. Multitasking is not the only solution. We have multitasking is one of how many? 1, 2, 3, 4 solutions for dealing with multiple processes. We have 4 solutions here. The multitasking is one of these solutions. And multitasking has another name, which is concurrent programming. Concurrent programming. We can also delegate specific real-time tasks to distributed intelligent data logging or control modules. For example, if the CPU don't want to deal with the interrupt, it can only not process data, but just save the data as logging and then give another system the control to deal with the system, with the data, the logged data. Okay, so it's like having multiple devices. This is, for example, this is multiple computer, multiple PCs. This is multiple PCs. One PC is doing some action, the other one is doing another action, and so on. The second solution is dedicated data acquisition cards with onboard memory buffers and intrinsic processing ability. So this is also another solution. We have data acquisition cards, and the data acquisition cards has onboard memory and buffers and simple intrinsic processing ability. This is also another solution. The third solution is use of a separate multi-processing computer system. This is different than the first one. This is multi-processing computer system, means we have multiple processors, many processors on the same computer. So the second so if we have process 1, this is assigned to processor number 1. Process 2 is assigned to another processor, and process 3 is assigned to a third processor. This is multi-processing. It's different from multi-programming. Multi-programming, we have a single CPU, and that single CPU is making round robin to have the ability of doing multitask. Okay, these are the solutions for concurrent processing. And the scheduling. We talk about interrupt because interrupt, we are dealing with real-time systems. We have to speak about the problems in the operating system that may affect that real-time processing. The first one we talk about interrupt, the second is scheduling. And the scheduling is the operating system process to allocate time to a various tasks, and this is known as scheduling. This is known as scheduling. So the CPU here, as you see in the figures to the right-hand side, we have a process 1. The CPU is switching to process 2, returning back to process 1, returning back to process 2, and so on. The scheduling has 2 types. The first one is non-preemptive scheduling, and the second one is preemptive scheduling. The non-preemptive scheduling to the right-hand side means the CPU is moving whenever it needs to switch. If you see, this is no interrupt. Here we have interrupt. The non-preemptive, there is no interrupt. The CPU is handling this task, and after finishing it, it moves to another task. Sorry, it's the same task. I'm sorry. This is process 1. So it gives a specific time to process 1, and then gives another time to process 2, and gives another time to process 1 again, and so on. So it is different from the primitive. You can say the primitive is more fair, more fair. You can say this is more fair than non-primitive interrupt. It's like non-preemptive is like saying, nobody disturbing me. I'm doing something, don't disturb. This is non-preemptive. I cannot see this. Okay. We should talk about the multitasking and threading. For the system to handle task switching, it should store the current state and handle the data of the new task. And of course, this is not feasible in real-time system. Sometimes we can have multi-threading. This is one technique of having the concurrent processing. The same process or multiple processes share the same data and the stack, and the task, the same process is divided to multiple threads. The same process is divided into multiple threads, and those multiple threads, they are sharing the same data and some stack data and some variables, or some code snippets and data. Okay, they share some code snippets and data. And Windows NT supports multi-threaded processing. The real-time design consideration. Okay. Would you like to have a break for 10 minutes? We are in the middle of the lecture. So if you want to have 10 minutes break, okay. Okay, guys, are you there? Anybody here?
موجود دكتور.
Okay, so after 10, we return back. I think time now is what? We return back at 9. It's 10 o'clock. We return back at 10 o'clock at your time, okay? Okay, inshallah. Okay. Just confirm with me. You hear me? We return back at 10 o'clock at United Arab Emirates time, okay?
طيب.
Okay, Ala, okay.
Okay.
I think you are the only one hearing me. حد معاه شباب؟ حد سامعني؟ بنات شباب حد سامعني؟
Yes, doctor.
دكتور معاك.
اوكي.
وعليكم السلام.
في اي سؤال او اي استفسار في الجزئيه اللي فاتت؟ any question about interrupts about anything?
لا يا دكتور.
Okay. For the next section, we'll talk about the real-time design considerations. The structure of real-time multitasking programs, how the CPU is doing multitasking. For example, here in the image, as you see to the right-hand side, we have a sensor for making, not to the sensor actually, this is manufacturing or producing rolled metal or polymer sheet or plastic sheet, like plastic sheet. The factory here is producing the polymer sheet, and there is some kind of sensors here. There is a sensor for measuring the thickness of the sheet, and another sensor for measuring, it is not in the picture, another sensor for measuring the temperature. And this is some kind of physical world, and we have the CPUs dealing with that physical world. If we move to the next slide, we have task one, which is spacing control. Spacing control means the thickness of the sheet, and task three here is temperature control, that control the temperature of the sheet. And we have task two here, which is important too, which is displaying data about the temperature and about the thickness. So this is measuring temperature, and this is measuring thickness, and the task two is displaying that data. We have here at a higher level the operating system and a preemptive scheduler. Preemptive scheduler means that it can be interrupted. So the operating system is handling task one, then moving to task two, then moving to task three. And this is the current task. It is only one processor, not multiple processors. One processor and dealing with multitask. So it switches between tasks. So it takes the first one, task one, and then move to task two, and then move to task three. And for each task, we have the physical world here and the interrupt handler module. This module is dealing with the outside world and taking data from the outside world to the data buffer, and the data buffer is moved to the it is moved to a process that deals with this interrupt. And also for the same for task three. But here at the middle, we have different scheme. We have different scheme here, which is dealing with the buffer or message queue. This is some kind of communicating between tasks. We have a process one, process two, and these should be communicated using messages. It's like message system. It's messaging between processes. For example, if task 3 has information about temperature, it should be transferred to task 2 in a message. And then it's like this buffer is displayed to the physical world, which is a monitor. Okay, and if some kind of control according to the data is transferred back to task this is not feasible here. You cannot control with the mentor, because here, as you see, the data is coming one way only. It's coming from task 3 to task 2, and coming from task 1 to task 2. So it is one way. It is for displaying data only. Okay? But the most important thing you should know is that the communication between these two processes are done using the communication is done using the messages. Okay? That's all about this figure. Just to understand that the operating system controls the tasks and switching between tasks, and then the one of the tasks is displaying data is one-way task, because data is coming from process 3 and process 1 to process 2, and this process 2 just taking this data and displaying it to the screen. So the inter-process communication, as I told you, it is done using the messages, is just like accessing a shared resource like a buffer or message queue that is maintained somewhere in the PC's memory. If multi-process needs to access the same resource, as you see here, task 1 and task 3, they are accessing the same buffer, the same resource. The same resource here is called critical section. In this case only, we can say this is a critical section. Of course, here we will not have a problem, because this is just displaying data. But if there is no organization of accessing this resource, maybe the temperature data is overwriting the spacing data. And this is going to be a problem. So we have to manage this critical section, and the operating system is dealing with critical section using something called mutex, or mutual exclusive. Means one task should be handling the critical system at a time. Only one task is handling the critical section. No multiple tasks handling the same critical section. It's like in our daily life, is like the WC. One person at a time getting into the WC. So if somebody else want to get into the WC, so he get out, like if you in the airplane or the uh, if you are traveling using airplane, and you see the WC has an how to say, has a light. This light is red. When this light is red, so the WC contains somebody. If the light is green, this means there is no somebody in the WC, and you can go to the WC. Mutex work in the same thing. There is a flag, and the flag is set when somebody access or take the critical section, and reset after that process leaves the critical section. And that flag in operating system, they call it semaphore. Semaphore. And I think you understand, or you heard about the semaphores in operating system subject. Semaphores are like trains in a train station. Some train stations contain only one track. So if a train inside the train station, there is a semaphore, like I can draw it. I'm not good at drawing, but let me draw it like that. This is semaphore. So here the semaphore in a status, this is the ground. This semaphore has no, the station has no train inside the station, okay? But when I don't know if it is like that or the opposite way around, but it is okay. One of them is for alarming or flagging that there is some train in the station. The other one is like that. Let me draw it. Some fixed to the ground. And the alarm, the semaphore is like that. Okay, this shape means there is no, I don't know if this means there is no train in the station, or this one there is no, one of them means there is no train in the station, the other one means there is some train on the station. It's like that, okay? This is semaphore. This is semaphore. And the semaphore, as I told you, is exactly if you travel using train or using the plane and you want to go to the WC, you find a light, and this light is red when somebody in the WC, and this light is green when there is no somebody in the WC. So we have to find a way, the operating system should find a way to deal uh, with the critical section. It is important. Why we say that? You are engineer, and maybe you will design some kind of RTO, real-time operating system, for your input-output application. That's why maybe you will face some situations that should deal with miotics and critical section. That's why it's important to explain to you. And also the deadlock. The deadlock means one process is accessing a resource and waiting for another process to release the resource. They wait for each other for endless time. This is a deadlock. It's like you wait for me and I wait for you. You wait for me, like two angry persons. They have fight together and then they go home. One of them waiting for the other to call him, and the other waiting for him to call him. It's like that. It's a deadlock. Deadlock means the system will hang on in one process, and one process is dealing with the system will hang on because one process is waiting for another process to release the resource, and also the other process is waiting for the first process to release the resource. They wait for each other. This is a deadlock, and you have to find a way to get rid of the deadlock. The priorities. Also, as I told you about priorities, interrupters needs some kind of priorities. So if we have a patient and this patient is handled by a nurse, nurse cannot be, cannot be waited, checking for the patient for every 1 minute. No, she should have some kind of interrupt, and this interrupt is like a button for alarm on the patient's bed. When the patient push this button, the alarm can heard by the nurse, and the nurse go to the patient. Just like that, interrupt. So sometimes the another interrupt is calling the nurse while she is surfing the patient. So this should have some kind of priority between interrupts. So to decide if the patient can leave, if the nurse can leave the current patient and move to the other patient or move to the operating system service or not. This decision is done according to the priorities. Actually, there is some kind of priority problem here is called the priority inversion. And this is like if the operating system is higher prior is dealing with higher priority process. Currently, it is dealing with higher priority process, and it is preempted by a lower priority process, and this is called the priority inversion. It's like the lower priority process is interrupting the higher priority process. This means the lower priority process will be of a high priority. It's like the high one will be low one and the low one will be high one. Is invergent. That's why it is invergent. Swapping rules. The high priority will be low priority and the low priority will be high priority. And this is problem happening in the operating system too. The last section here, we talk about how to implement real-time systems on the PC. We will talk about the operating systems. MS-DOS and Microsoft, they were not designed for real-time systems, actually. So they contain the two common problems, which is interrupt latency and reentrancy. And those kind of operating system, they are non-deterministic. This means they cannot expect the latency time. They cannot expect the time needed to reply to the interrupt, the time needed to switch between tasks. This is not deterministic. You cannot guess it. You cannot guess this time using the operating system like Windows and DOS, because why? Because they are not designed for real-time interaction with physical world. They are designed for multitasking and multiple users. The use of buffered data acquisition and control cards, hardware triggering, autonomous data loggers, specialized RTOs increase sampling rate and reduce time. This means we can have Microsoft Windows as a higher level, but we should expect higher latency. We can go down, as here in this table, we can go down and use just hardware. We go near to the hardware to have more faster processing of data and higher resolution of our samples. For example, in this table at the top level, Windows 8 and Windows NT, they have very high time for processing. But if you go down, you'll find RTO, which is real-time operating system, and the hardware triggered and buffered analog to digital cards, and isolated input-output cards. They are more faster compared to Windows 8 and Windows NT. And these are the applications needed. This is samples of the applications, and this is the sampling rate. And as you see, the sampling rates are increased. The more you go near the hardware, the more you increase the sampling rate. And the more you go to the hardware, near the hardware, the more you reduce the time needed for dealing with input-output devices. The BIOS. The BIOS is an abbreviation of basic input-output system. Okay, let me ask you a question. Can you tell me anybody knows anything about BIOS? You tell me about it. Anything.
دكتور
Yes.
هو الاوبريشن او البروجرام بيطلع لك بالكمبيوتر اول ما تشغله، اول ما تدخل على ويندوز، اللي هو بتقدر تتحكم بالانستراكشن تبعت الكمبيوتر نفسه، اللي هي الاعدادات الاساسيه. هذا اسمه البايوس. غير الويندوز له اعدادات خاصه فيه، تدخل عن طريق يعني اول ما تشغل الكمبيوتر فيه كبسات بتدخل عليه مباشره. هو ما له علاقه بالويندوز ولا له علاقه باي شيء بالكمبيوتر، اللي هو انه برامج عم بحكي، بس هو له علاقه بالانستراكشن الاساسيه تبعت الكمبيوتر.
تمام.
دكتور، الاوبشنز بتاعت الاوبريتنج سيستم مثلا زي سكيورتي بوت او
أيوة.
ستارت اب، فهي الاوبشنز بتاعت الاوبريتنج سيستم نفسه.
اوبشنز الاوبريتنج سيستم. طيب
دكتور فيك تحكي الانستراكشن او الداتا.
البايوس هي في فانكشناليتي انت قلتها بالاشتراك معاك انت وعبد الله احمد. هي ان يبقى فيه اللي هو البوت، يبقى فيه انستراكشنز للبوت. البوت اللي هو ان انا انقل الاوبريتنج سيستم من الهارد ديسك للرام. ففي بروجرام اسمه البوت بروجرام، يعني بيبدأ عند البايوس. طبعا هو ما بيخلصش عند البايوس، لكن هو بيبسيط حتى البوت نفسه، السيكونس بتاع البوت نفسه نصه عند البايوس والنص الثاني عند الاوبريتنج سيستم.
دكتور هو بيعتبر مثل عقل الكمبيوتر، يعني عقل الكمبيوتر نفسه هو هذا القسم بيكون يفترض. صحيح؟
يعني لا يعني هو ممكن تقول كده. هو كده شفت المفتاح بتاع السيارة؟
ايوه
لما تحط المفتاح بتاع السيارة كده في الكونتاكت وبعدين تشغل السيارة، قبل ما تشغل السيارة كل ده بيحصل مع البايوس. أول ما تشتغل السيارة خلاص الأوبريتنج سيستم هو اللي يتحكم. بس بقى يعني المعلومة دي مش كاملة. يعني المعلومة دي ناقصة حاجة. إيه هي الحاجة دي؟ أقول لكم عليها. ودي أنا يعني أنا ما كنتش أعرفها غير لما دخلت الكلية زيكم كده. يعني أنا ما كنتش أعرف المعلومة دي. أنا كنت فاكر البايوس بيبقى في البداية بيعمل البوت وبيتشيك اذا كان فيه ميموري، فبيعمل صفاره اذا كان مفيش ميموري، الحاجات اللي انتوا عارفينها دي. لكن انا استغربت جدا لما دخلت الكليه وشفت المنظر ده. هوريكم المنظر. شايفين دي this is the application level and this is the operating system which is DOS for simplicity. And we have here the BIOS. BIOS is dealing directly with the hardware. And BIOS also is a level of dealing with the communication between operating system and the hardware, but not all the hardware is input output hardware. يعني مش كل الهاردوير البايوس بيقدر يتفاعل فيه مع طبعا عبد الله احمد قال جزء من الكلام ده. فهو بيتعامل مع الانبوت اوتبوت. يعني مثلا المذر بورد عليها كارد للمونيتور مثلا، او كارد تي في كارد مثلا. فالبايوس بياخد الداتا، بيتعامل هو بيكون الوسيط ما بين الكارد ده وما بين الاوبريتنج سيستم.
دكتور فينا نقول عنه الكومبايلر.
الكومبايلر حاجه
نفس
ثانيه.
الجزء؟
لا الكومبايلر حاجه ثانيه.
غير.
الكومبايلر حاجه ثانيه خالص، بعيد عن البايوس. البايوس هو يعني نقول هو بياخد من الاوتسايد وورلد ويدخل للاوبريتنج سيستم، والعكس بالعكس. يعني ماشي الطريق ده من الانبوت اوتبوت هاردوير ويدخل للاوبريتنج سيستم، والطريق العكسي انه ياخد بيانات من الاوبريتنج سيستم يديها للانبوت اوتبوت هاردوير. فيعني ايه البايوس مش مجرد ان هو بيعمل البوت سيكونس الاولاني، لا بيعمل كمان بيفضل معانا شغال لما الاوبريتنج سيستم يكون شغال. ودي انا اصلا زي ما بقول لكم ما كنتش اعرف المعلومه دي غير لما رحت الجامعه وعرفتها. يعني انا عندي كمبيوتر وعارف الكلام ده، لكن لما دخلت الكليه وعرفت ان البايوس برضه ليه دور في الاوبريتنج سيستم، مش مجرد ان هو بيباصي للاوبريتنج سيستم وبعدين ينعزل عن الايه، عن الاوبريتنج سيستم، بيفضل معاه ياخد من الانبوت اوتبوت انترفيس يدي للاوبريتنج سيستم، والعكس بالعكس، الطريق العكسي كمان. فبيزك البايوس اللي هو basic input output manages data flow between the computer's operating system and attached devices such as hard disk, video adapter, keyboard, mouse, and printer. This is done using BIOS. BIOS is not just used for the first boot or the first instructions needed to boot the computer, but also it contains working, it continue working while the operating systems work. But actually BIOS can be a problem, can be a source of a problem in real-time applications, because we are dealing with operating system clock. The speed of operating system, this is going to be a problem. We need a real-time operating system. Some of the BIOS services can suspend interrupts for unpredictable lengths of time. Some of the BIOS may also be non-reentrant. This means we have some BIOS problems. Maybe the BIOS, because the BIOS is dealing with input-output interrupt, dealing with input-output, that's good. That's very sufficient for us. It's good. We need it. But actually, BIOS is interrupted by another operating system services, and that's why it is not ideal for making a real-time operating system. Disk operating system, or MS-DOS, it works in real mode. Real mode means one process, and this one process handles the hardware or control the entire hardware. That's real mode. It is non-reentrant. Non-reentrant means there is no multiple interrupts and multiple returning from interrupt like that. It is one process, and this process is handled or controlled. The disk operating system control the entire hardware using this process. And also, I told you it allows the operating system services interrupt. Only that. There is nothing else. And it doesn't process multitasking and capabilities. It doesn't have multitasking capabilities. And also it is inexpensive. And most of the input-output applications use DOS because of this. That's why if you go to any factory, you see machines, and the machines have a screen. The screen will look like that one. This means the operating system is DOS. This means it is now, like if the machine that is controlling the sheet, the roller sheet or the polymer sheet, it will have a monitor like that one. That's why this means if you see this screen in the factory or attach it to a machine, you should know that the DOS is the operating system that is currently running. Why they use it? Just because it is in real mode, and it is non-reentrant and doesn't have multitasking. Okay. Of course, we can have our own real-time DOS. There is something like that, real-time DOS. And this real-time DOS is handling multitasking for input-output processes. Okay. And about Windows, the programs running under Windows, they execute under the control of the operating system. So, for example, if I want to have my own application for input output, dealing with input output, I should be working inside the operating system as a process. As a process, it should be working inside and limited to the or affected by the features of the operating system. They have restricted access to memory. This application that I need to have for input-output interface should be, or they have restricted access to memory and input-output ports and interrupt subsystem. They don't have the capability to directly have memory access or dealing with input-output ports and interrupt system. They also should be concurrently working together with other processes inside the system. So the process will not control the entire system. It works in parallel with other processes, and this means it doesn't have good latency needed for the real-time DANC. Also, Windows virtualization is good for isolating applications from the hardware, but it is not good. It is not good in real-time applications because it introduced additional overhead in working with real-time systems. Virtualization is good because it separates the user or separates the applications from the hardware, but it is not good if I want to have real-time application. For Windows, they are divided into most commonly used rings 0 and 1 and 2 and 3, but you can say 0 and 1 they are referred to ring 0, and 2 and 3 they are referred to ring 3. And if you see to the right hand side, we have Windows 98 and 95. By the way, I worked on these. I don't know if you worked on 98 or XP. Windows XP stayed for a long time, but I don't know. You are younger than me, so maybe you didn't see Windows 95. Anyway, I saw even Windows 3.1 at the college, 3.11. I didn't see 3.1, but I saw 3.11 at the college. At that time, it is 2000, sorry, 2000. At that time, I saw Windows 95. It was at the beginning of it. Now we have this figure, and this figure is divided into two parts, the lower part and the upper part. The lower part is ring 0, and this is the, you can say this is the kernel of the operating system. Okay, this is the kernel of the operating system, and it has highly privileged operating system routines and drivers. This part has highly privileged. It means that if you, as a user, played with these files, the operating system will be down. Here we have ring 3. The ring 3 is nearer. It is part of the operating system, but it is nearer to the user. Like user interface, like memory manager, task scheduler, and file input output. And also the ring 3 drivers. This is .drv. If you see, this is .drv means it is used by the user. The user can install the drivers for different input output devices. But here, this is device driver VXDs, means that it is for the operating system. The user doesn't have direct control over it. If we move to Windows NT, Windows NT is different. Ring 0 is bigger. You see, it is bigger than the ring 0 in Windows 98 and 95. So Windows MS Windows here, ring 0 is bigger, kernel mode is bigger, and the privileged of the mode is bigger. It contains mostly 90% of the operating system modules like Windows Manager, Graphic Device Manager, Input Output Manager, Process Manager, Virtual Memory Manager, and microkernel. This is another kernel inside the bigger kernel that deals directly with the hardware in a hardware abstraction layer that separates between the hardware and the microkernel. So this is Windows, but this is Windows NT. So this is different. You can say this is more secure than the Windows 98 and 95 because Windows NT is designed to deal with the internet and they want to separate most of the operating system routines from the user. And that's all for today. If you have any questions, I welcome
No,
you if you
Doctor,
have any
thank you.
questions.
Doctor, thank you, Doctor.
Okay.